Ideal gases have another behavior, and that's density. And density impacts their ability to float, as you learned from your regular Coke or your regular soda and your diet soda experiment, I hope. Let's explore that a little bit more. We start with what you know, and then we move into the more complicated stuff like we usually do. How does density impact soda? Well, you found out regular soda sinks in water. Why? Part of the reason is density, not the whole reason. Density is mass over volume. The mass of the regular soda had water in it plus sugar, so the mass was greater than just water alone in the same volume. So the density of the regular soda was greater than the density of the water in the same volume. So what is density anyway? People really get confused about it. We're going to set it all straight. Think of density and buoyancy. Lighter densities can float. The mass of the pine wood in that canoe is lighter than the mass of the water in an equal volume that fits in that canoe. And because the mass of the pine wood is less, the density of the pine wood is less than the density of the water, and the pine floats on top of the water. Conversely, lead. The mass of lead is far greater than the mass of water for equal volumes. And because lead structure has no air at all, and it has molecules with very high mass, then the density of lead is going to be far greater than the density of water. And so lead will not be able to float on top of water. Lead will sink like a balloon. But you say, how do we get ships to float? We can have huge container ships. How do we get them to float? They can be so loaded down, it's really quite a miracle. And lead can float because density is not the end-all and be-all to buoyancy. Density is important, weight is important, but pressure determines buoyancy, and pressure is weight over area. So these ships have enormous lengths and huge widths so that they can take up an enormous amount of area as they contact water. And in taking up that, they displace less water, and that they have less pressure down on the water from their ship. They're riding higher because they even have more pressure from the water pushing up. So when you are creating a large area here, you are reducing the pressure on the water. And that's how container ships full of metal can float. Hope that helped you out. Let's look at density and altitude now, and flotation in altitude. So you know that density is definitely a behavior of gases. How does that impact baseballs? Two different fields. Coors Field in Denver, Petco Park in San Diego. If you're a home run hitter, where can you hit a ball farther? Scientific fact. Two parks at very different altitudes. San Diego is at sea level. Denver is at about, I believe, 5,000 feet, maybe 6,000. How does gravity impact air? Impact air density? Remember, higher altitude, lower gravity. All right. Denver is high. And remember, with that lower gravity, you get less compression. And with that less compression, it means that there are less molecules and less mass in the air in Denver. You have less molecules and less mass in the air in Denver. So the air in Denver is less dense. And when you hit a ball, it has less molecules to slice through in order to really fly farther. In fact, if you're in Denver, that means that your ball can go an average of 10 meters, which is approximately Yeah, 30 feet farther when you hit it with the same force. It's also a reason why Denver really hasn't had a lot of championships, because their hitters get used to, physiologically, they get used to hitting less far, and they have a hard time hitting home runs on away games. Kind of cool, huh? Density and humidity and floating is important as well, and it becomes more important to weather. So how does air density impact the atmosphere? Well, let's say I had a scenario here where you're going to a friend's party and you can't buy helium. There was actually a shortage of helium earlier in the year. What are you going to do? You need birthday balloons. So you get a friend to help you. You decide to blow them all up. And you decide to blow into yours. And she says, forget it. I'm getting a bicycle pump. And then you decide, all right, to make them float, we're going to put fans underneath them to push up on the air to make them float. Okay, you're good. You're good. Which of those balloons is going to rise higher? Is it going to be the balloon that you blew up with your air, which has a lot of water vapor in it? Or is it going to be the balloon that you blew up with the bicycle pump, which has relatively dry air in it? And I'm back now. You know that your breath has water vapor, and it seems logical that the dry air would be less dense, and the dry air balloon should float higher. But you might have noticed that if you ever walk into an office building, the higher floors actually feel more humid. It's really common for them to feel warmer, but sometimes you can detect a change in humidity in the higher floors. The reason is that humid air floats. Humid air is less dense than dry air, but I have to convince you of that because it doesn't seem to make sense. And what does make sense is you could say air with water vapor condenses and rains down. So why would humid air rise higher than dry air? And I want to explain that a bit to you by talking about an observation and another scientific law. The observation is something that you know, that all of these balloons that you blow up are going to have basically the same volume. That's your observation. You can go just so far with those. And there's an Avogadro's law that says for the same volume of ideal gases at the same temperature and at the same pressure, all of those gases will have the same number of molecules. So each balloon has the same number of molecules in it as any other balloon. And this is important because when you have humid air, it can be at a maximum of about 4% water vapor. Any more than that, it's going to condense out and rain. So at low concentrations, this density of water vapor is much less dense than the density of liquid water, which is much more dense. Obviously, it's 100% water. And the fact is that that density is so much less than water and so much less than atmospheric nitrogen and oxygen. So water vapor is really very low density, and when it evaporates, it's warm as it evaporates, and it rises into the atmosphere and displaces other parts and other molecules in that same atmosphere. So as water comes in after it evaporates into a volume, it pushes heavier molecules out. And in pushing those heavier molecules out, the humid air actually becomes lighter because it has less heavy molecules in it at this time. Now, a balloon has less nitrogen in it with water vapor and less mass and less density, so it floats higher when it's humid, and balloons with the humid air will float higher. What does this mean for meteorology? Well, this is a barometer, an aneroid barometer, that most sea captains have in their living quarters. And you can see in here that falling pressure indicates stormy weather. Okay, falling pressure indicates stormy weather, and we know that the density of humid air is less than the density of dry air. And density is mass over volume, and weight is mass times gravitational acceleration. And pressure is weight over area. So when we have less density, we should have less pressure. Guess what? Humid air has less mass, it has less density, less weight, and less pressure than dry air. So this aneroid barometer will spin around to show lower pressure, generally at 28 inches, or if you're doing metric, around 960 millibars of pressure, that forecasts stormy weather. Probably more like 985 millibars that forecast stormy weather. I hope this helps you out. I hope that you really internalize this, because this is an important lecture. It's going to come back in climate change. We'll talk soon.